Welcome to everyone who's joining us online. Like I said a little bit earlier, this review session is like a lot of Q&A. We can just kind of go through and search for some practice problems if that's what you really want, but mostly I kind of do it based on like what you guys are struggling with or what you guys want to review before the exam. So if anyone has anything that they want to talk about at any point in time, just let me know. Let's find some limits. Why don't we do that? I'm currently on page 97 in the book, and this is the chapter 1 review. And let's do squeeze theorem and definition of the derivatives and related rates or worst. Okay, let's do that then. Let's do a couple of these practice limit problems. Let's just do 20 limits with trig. Okay, let's do 25 then. Okay, so here we have this limit, the limit as x goes to 0 of cos of the quantity x plus sine x. So this is kind of a nasty looking one, but basically what we're going to do is just sub in 0 for these x values. So I'm just going to go ahead and write. So if x is going to 0, then we're going to consider that to be 0 plus sine of 0. And what is sine of 0 going to be? Okay. Then what this is 0 plus 0. So we're going to write this down as cos of 0. And what is the cosine of 0? 1, exactly. So this is just going to be the limit, or the limit is going to equal. Okay. Then they didn't decide to put a lot of trig functions here apparently in these limit practices. So I'm not seeing a lot of the trig limits here on 97. So I'm going to try to find some of these other problems that we were talking about. The definition of the derivative, you said, is another thing that you were struggling with. What section is that? That's are you struggling with it in terms of like the limit as h goes to 0, like definition wise? Okay. All right, there is a really good way of envisioning this, I think. Give me just a sec to find the graphic I'm looking for. Okay. I'm not sure where the graphic is, but let's see if I can remember it and just kind of draw it out. Basically, what's going on here is, this is not on any page, we're just kind of talking about the definition of a derivative in terms of the limit as h goes to 0 of f a plus h minus f of a over h. And so I'm going to write that whole function out right here so that we can kind of take it apart piece by piece. Sorry, I've been working on writing my F's so that you guys don't get them mixed up. All right. So basically, we have this function, right? And this function, we'll say, looks like this. Actually, I don't like that. We're just going to call it some sort of curve. So now this function looks like this. So this is x is equal to a, right? So this point right here would be f of a. And this point right here, we're going to call this distance h. I'm going to try to do a little bit of color coding here maybe so that it's a little bit more visual. And then that will make this point a plus h. It's because it's the point like a, x is equal to a, plus some distance h, and we end up with the point a plus h. Yeah? Just let me know if at any point you're not following where I'm going with this. So this will be the point f of a plus h. So basically, there are two ways to think about what a derivative is. There's like the algebraic way of thinking about how a derivative is, and then there's a geometric like form of thinking about like what a derivative is, right? Algebraically, how we're going to think about this is in terms of the derivative being the instantaneous rate of change. Let me make this a bigger screen. Sorry, I'm moving the group chat around. Okay. You guys are familiar with that? The derivative being the instantaneous rate of change? That would put it in direct contrast to the average rate of change, right? Which is the like, if I were to represent the average rate of change on this graph between a and a plus h, what would that look like? If I were to represent graphically the average rate of change on this graph right here, what would it look like? The average rate of change between 2 points you can find out just by drawing a line between them. And then the average rate of change is this slope. You follow me so far? Awesome. Okay. So basically what we're doing here is we have this point right here, which is a, what this is a comma f of a. So the y value here is f of a, and the x value is a. So the point is a comma f of a. I should have written that better when I drew it out the first time, and I did not. So, and this is f of a plus h, and this is going to be f, or a plus h, comma, f of a plus h. So basically what's happening here is we have these 2 points, and we're going to relate them initially by an average rate of change. And the way that we're going to determine that is by the slope of the line between the points. And the slope of the line between the points is delta y over delta x. Very basic, like, line stuff. So the change in y, which is going to be f of a plus h minus f of a, right? We go from f of a to f of a plus h over the change in x, which is going to be a plus h minus a. And what we're going to do here is we're just going to get rid of both of those a's. We're going to have a minus a. So the average rate of change is going to be f of a plus h minus f of a over h, which we know is familiar because it's this right here. So we figured out what that chunk of the equation is. This is an average rate of change. And it's something that you've encountered and worked with before. What's new here is that we're introducing the concept of limits to this, right? We're talking about now, as the limit of h goes to 0, what happens to this whole equation. And what that's going to actually look like is, let me erase some parts of this graph. We're going to be changing our f of a plus h. Let's consider that f of a, or a f of a stays the same. So we're going to use the same graph. We're going to use the same point a. We're just going to change what h is. And to do this right away, we're just going to make h a little bit smaller. So instead of h being all the way over here, we're just going to say h goes to right here, right? And so now, use color, it's a little bit different. Use this blue. So this is going to be a plus h, this point right here. So this will be f of a plus h, and this point will be a plus h, f of a plus h. So I have a line like that. Okay. So I had something going on up here. This is my original. And now I have this blue line here. I have this tinier h, and I have a line that is a more accurate representation of the rate of change that's going on at point A. The smaller gaps that we take, the more accurate this is, which you can kind of visualize based on this graph, because if we go from this point to this point, it's a very dramatic change in x value and y value, and there's all of this gap. So it is an average rate of change, but it doesn't really tell us what's going on in the graph at any of those points. We just kind of know averagely what's going on. But if we want to look at what's actually happening in the graph, maybe a better way to do that is to have a smaller h, so that this blue line pretty much rides right along that black graph. And so we can kind of glean from that it's a little bit more accurate in telling us what's going on in the graph at that time. That being said, it's not as accurate as it could be. I'm just going to rearrange these labels a little bit again. And so that's the point. Now we're going to make h even smaller. So now this is h. This is going to be a plus h. This is going to be the point. This is going to be like that. And in principle, what is going to happen is that h will continually be smaller. So h is approaching 0, right? H is going to get really, 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 really small until it's basically what's going on at A. And what's going on then is we'll have a line that is tangent to the curve. So basically, the slope of that line, if we were to continue this orange line and this blue line, they would kind of, represent what's going on in the curve, right? We're kind of simplifying the curve to a line. And the reason we do it between points is because we want to make it clear that this is not like a great representation of the line at any other point in time. But what's happening with this pink one is that at this point, A, we're saying that this is a great representation of how the curve is changing. Because it is the instantaneous rate of change, because h is approximately equal to 0. So basically what's going on here is that we have h getting smaller and smaller and smaller, and eventually a plus h is approximately equal to a, and that's kind of when we say, okay, so we've got this instantaneous rate of change. Because we're looking at an average rate of change in principle, but the distance between the points is so, as they say, arbitrarily small that we're capable of analyzing it as an instantaneous rate of change. Does that kind of help? Is that the kind of question you were having regarding the meaning of this limit equation as the definition of the derivative? Okay, yeah. So basically, the way that I think of derivatives is we've got our geometry of it, which is a derivative is the tangent line. And then we've got the algebra of it, which is that it's the instantaneous rate of change. And kind of the point of what we're doing here is being able to represent that with greater and greater accuracy, eventually getting to the point where we can just take the derivative using the chain rule or something like that based off an equation. But keep in mind that there's always a way that we could revert it and graph it and figure out the tangent line to the curve, and that's going to be the derivative. So, yeah. All right. So, I'm going to clear this. And we also were saying that we had some issues with related rates, which is, I think, at the end of chapter 2. Yeah, I don't know. I struggle to read through like math textbooks, at least I do, because it seems like there's like so much going on and it's so dense, and sometimes it's just easier to like piece it together as like what exactly is going on with this, like in this equation, and how can I relate that? Yeah, videos, it's so valuable to go to lecture. It's so valuable to go to lectures. Just because, I don't know, I just really struggle with the book. Okay, so related rates is, I guess in my calculus class, we called it optimization. And this is the biggest struggle that I probably ever had in calculus, because it's all applications. So let's try a few optimization problems. I still work through them pretty slow, so of course feel free to just drop in the chat box and tell me like exactly what I should do next. And we're going to get through a couple of these. So currently I am on page 185. This is chapter 2, section 8, related rates. So what kind of a question would you like to kind of do? Maybe the spotlight question, like maybe 18. Two objects moving away from each other. Maybe 17. Or 16. It's up to you, my dude. Oh yeah, no problem. This will put us on 186. Oh yes, no, I do too. It is horrible to navigate. It's the worst. $16, okay. So at noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Hoofda. All right. So how I approach optimization problems is determining what I need or what I want and what I have. So let's start off by kind of listing what I have. I have a diagram that I'm going to kind of sketch. So this is going to be ship A, and this is going to be ship B. And I know that this distance between them is 150 kilometers. And ship A, I know, is sailing east. And that is going at a rate of 35 miles per hour, or kilometers per hour. I'm just going to kind of draw an arrow. And B is going north at 25. Okay. So how fast is the distance between ships changing at 4 p.m.? So what I'm going to kind of determine now is in 4 hours, how far did ship A go? I'm going to convince Zoom to let me open a new tab so I can put that in the calculator. So 140. So ship A and then ship B we're just trying to figure out now like where they are in relation to one another. So I'm going to kind of sketch this diagram at 4 hours later. And I'm going to erase this initial one that I drew, partially because it's cluttered and partially because I want to draw a little bit bigger now. And then okay. So 150 was initially the distance that they were separated, right? We had A over here and then B over here, and they were 150 kilometers apart. And then A started going this direction and B started going this direction. So A went 140 kilometers east. So now the difference between them, like horizontally, is just 10 kilometers. But B is 100 kilometers more north. So the distance between these two ships is just going to be the hypotenuse to this triangle. In this case, it is going to be, I'm not sure if we need this information, but I'm going to find it out anyway, just in case we do need it. It's going to be 10 squared plus 100 squared square root. This is just Pythagorean Theorem. So that's 100 plus I'm going to find the square root of that. And the square root of that is 100.499. Okay. So this distance right now is 100.499 kilometers. All right. So now we kind of know what this triangle looks like. This is information that we know or that we were able to glean from the information that we were explicitly given. What we want to know is how fast the distance between the ships is changing. So we want to know this number here in the purple, how fast is it changing at 4 p.m.? So to do that, let's see. We are going to be taking some derivatives with respect to time. We need to build ourselves an equation out of something. I'm going to write down what we want right now. Okay. So, if anyone has any suggestions, feel free to just go ahead and put it in as to how we should set up this equation. Good one. Okay, so the equation that we have is the Pythagorean theorem. So let's use that to figure out what's going on. We know that our number, right, is going to be this c, and that is going to be equal to the square root of this distance. Let's see how we put it together, containing the changes. Okay, so let's call this, we're just going to call it x squared, and y squared, okay? I'm going to start off like that. And then we're going to put this in terms of something else. We're going to call this dx dt, and we're going to call this dy dt. Okay? Because this is going to be the change on this x-axis, and this is going to be the change on the y-axis. So A is moving horizontally and B is moving vertically. And then this is what we actually want, this length. But rather what we want is the distance changing with respect to time. So that is going to end up being dc dt. Okay? All right. So now we need to differentiate with respect to t. And some things to know. You guys went over implicit differentiation, right? Awesome. Okay. Both of these are functions of t. So they're not going to be considered constants. We're going to have to use like implicit differentiation to work with them. Okay. So let's do this. We're going to take the derivative of both sides. So we're going to end up with dc dt, that's what we wanted, is equal to, I'm going to rewrite this to the 1/2. All right, now we need to go ahead and use some of our derivative rules. How am I going to take that derivative? Yes. I'm going to be using the chain rule. So I'm going to say that g is equal to x squared. This is going to be, g is a function of t, technically. And this is going to be x squared plus y squared, both of those being functions of t. Then g prime of t is going to be equal to, what is this going to be? To x dx dt plus 2y dy dt. Exactly. Here we have f prime of g is going to be equal to 1/2 g to the negative 1/2. Okay. Now we have all of the information we need to put together the chain rule answer. It is going to end up being 1/2 and g is equal to x squared plus y squared to the negative 1/2 times the quantity 2x dx dt plus 2y dy dt. Awesome. And so that is going to be dc dt, which is what we want. This is our answer. So now what do we do? What do we do with this long string to get an actual number out of it? Get 2 out of g prime. Yep, we could do that. So algebraically, just to make something simpler, this is going to turn into 1/2. And then that 2 and that 1/2 can be canceled. So it will end up just being like this, which makes life simpler for us. Yep, we plug in the values. So we have x being equal to our x value right here. So that's 10 squared plus 100 squared to the negative 1/2 times 10. And then we just picked out dx dt and dy dt. Dx dt is going to be 35 kilometers per hour. And dy dt is going to be 25 kilometers per hour. So we know that this is 1 over 100.499. Then we have this is times 10 times 35 plus 100 times 25. It's 100, missed a 0. And that is what? Times, that's it, 850. And I'm just going to, in order to avoid a calculator, I'm going to call this approximately 100. So the answer to this is approximately 28.5. And what are my units? Perfect. Cool. Okay. So, like I said, I struggle with these types of problems, but basically you just need to figure out what you have, like what was given to you by the problem, work through all of that, then figure out what you want from the problem. And then turn it all into math language, which is this dx, dt, dy, dt stuff. And then work with it. A lot of the times for these optimization problems, you will be asked to differentiate with respect to time, because a lot of these problems are kind of real-world examples and involve a lot of changing the time. Okay. Do you guys want to do another optimization problem? Okay. Let's do you want to do another ship problem? or maybe number 30? Actually, no. Well, yeah, number 30 could be useful. What do you guys think about 30? This is on page 187. See, my unfortunate position is that I have not GSG'd for 140 before, so I'm not entirely sure what your professors like to put on their exams. So I don't want to pick a really, really random one that is something that your professors would never consider. Let's do another ship one, because that's a really popular one that I remember on a lot of my exams. I'll have a conversation with Kasha about what exactly is going to be on your guys' exam and what I should focus on really soon here. Okay. Let's do 30. Okay. This is page 187. So we have a kite that's 100 feet above the ground, and it's moving horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? Okay, and so I'm saying that it's moving horizontally in this direction because this angle is going to be decreasing. And so I'm kind of envisioning that as time goes on, it's going to be like a smaller angle, et cetera, et cetera. So that's why I drew it going in that direction. All right, so you guys tell me, what am I looking at? What kind of equation should I be using? Yes, exactly. Awesome. So what we want is d theta dt, where theta is our angle here. So we want to know at what rate that angle is changing. We can use sine to find it. Awesome. Perfect. Okay. So that equation is going to be sine theta is equal to opposite over hypotenuse, right? Our hypotenuse in this instance is going to be right here. It's going to be 200, right? Because we have this right angle going on. So our hypotenuse is going to be 200 feet. No, actually, our hypotenuse should be changing. Will it be changing? Yes, it is. Our hypotenuse is going to be changing. What is constant is our opposite side here, which is going to be 100. because we're moving horizontally this direction, so our hypotenuse will be growing longer, but our height above the ground is going to remain 100 feet. Yep. Okay. So the hypotenuse is not changing at a rate of 8 feet per second. The horizontal is changing at a rate of 8 feet per second. That doesn't give us the rate that the hypotenuse is changing. So we might need to do like equation with an equation here. 100 over x, what do you mean? Are you talking about this length here as x? Like we could do that. I have a tendency to just leave the horizontal being x and picking another variable for this. I was going to put in like c again because like we did in the last time, mostly because that kind of shows that this horizontal and this length right here are different. Does that make sense? Because I fear that if I put x in there, then I'll get confused. So I'm just going to call it c, like in the Pythagorean theorem. So in order to find the rate of c changing, we're going to need to do essentially what we did before, I think. So c is equal to, or rather, let's just figure out what's going on here. Let's just try to take what we have and do what we can with it. In order to get theta on its own, we're going to need to take the inverse sine, I think. Does that make sense? And so d theta dt is going to equal and c is a function of t. All right, so how do we take the derivative of inverse sines? Sorry, I get very confused between what material is covered for 141 and which one is covered in 140, which is really unfortunate because we were just talking about this kind of stuff, but I think it was in 141. So do you guys know how to take the derivative of the inverse sine? Have not covered that yet. Then I doubt that they would be having you do it. That wouldn't make any sense. How would you guys approach the problem? So where would you go from here? Find a value for the bottom? Okay. because we have two values already. Okay. So how do you want to do that to find that value for the bottom in this C of t? So in this case, we're going to have to do essentially the same thing as before. Okay, so what you're suggesting we do is directly do x squared plus 100 squared is equal to 200 squared. Do you want to put that in a calculator and figure out what x would be? Yeah, you can't use calculators on exams, but a lot of these problems, I mean, you can leave it as a radical if you want to. A lot of these problems, though, are kind of in the book, are designed to be solved with calculators. So as long as you kind of are familiar with like algebra, like functionally, then I would say it's fine if you use a calculator to solve these types of problems. So I got like 173. Yep. Okay. Okay, so we would put that here. And now what would we do? Because remember, this is for C. This is sine is equal to opposite over hypotenuse. And our hypotenuse is this 200 feet right here, right? So we can do tangent. We can do tangent. So that would give us a pretty good snapshot of, so tangent is opposite over adjacent. So that would be 100 over 173.205. So we would have theta is equal to tan -1 of this number. Which is 0.577. What would happen then? This is a really good way of like attempting to solve problems, is just to like go ahead and try stuff. So we get what theta is equal to. So theta is going to be equal to a number, right? And then what do we do? What is d theta dt going to be equal to if we take that derivative? Nope. If we just take the inverse tan of this number, the inverse tan of the number, there's no variable involved here. So theta is equal to 0.52336. So we would take the derivative of that, and we would end up with d theta dt is equal to 0, because this is a constant. Yep. So using tan is a good gut motion, good like reaction, but our end result is just going to give us 0. It's not changing, because we're not taking into consideration that it is changing. This angle is decreasing, because this string length, this 200 feet, is not going to be 200 feet in the next second. It's going to be 208, or not 208. It's going to be some other number, because we're moving 8 feet per second horizontally. Does that make sense? Why we're not going to just use the tangent? Yeah, because we want to be able to use the fact that this is changing to better describe the system that we're working with. So what we're going to do is like the exact same thing that we did before. We are going to have g of t is equal to x squared plus y squared. G prime of t is going to be equal to 2x dx dt plus 2y dy dt. F of g is equal to g to the half. F prime of g is equal to 1/2 g to the negative 1/2. And we're going to put it all together to get the same derivative. C prime of t, the changing of this number, this length right here, is going to be equal to 1/2 x squared plus y squared times, or to the negative half, times 2x dx dt plus 2y dy dt. Okay, now let's go ahead and put some of these numbers in. This is going to be 1/2 x squared in this instance is going to be 173.2 squared. So do I need to do this? I do not, because we've already determined, right, that x squared plus y squared to the half is going to be 200. Right? Because this is 173 squared plus 100 squared. Square root of that is going to be 200 by definition. So what this is 1/200, because it's a negative now. Do you see what I did algebraically there to save myself some heartache? Awesome. All right, so then this is going to be 2, and then x, which is 173.205, times 8 feet per second. 8. Plus 2y times 0. My y value, we've decided, is not going to be changing. We're still going to be 100 feet off the ground. So I'm just going to say plus 0. So this is going to simplify a little bit to 1/400 times 16 times 173.205. So we're going to figure out what that is. As soon as I put this in. So this is going to be, and then divided by 400, going to be 6.928. We should have called it 6.93. So now we know that C is changing at a rate of 6.93. So this hypotenuse is getting longer every second at a rate of 6.93 feet per second. Let's see how that can be useful. Okay. So my issue is that you guys don't know how to work with the sine inverse, like taking a derivative of sine inverse. And okay, let me just kind of work some stuff out here. This is going to be, if I just take it with respect to t, I would end up with what? Cos, this is theta of t. So cos theta dt, or cos theta d theta dt, just like I would, is equal to 100 times the derivative of 1 over c of t to the derivative of c to the negative 1, which is equal to what? Negative 1c to the negative 2 times dc dt. Ha! We got it, guys. Ha ha. Do you see what I just did? I think I just did implicit differentiation to figure out basically the derivative of this with respect to t, and I ended up with cos theta times d theta dt, something I want that very much, which is equal to 100 times negative 1 c to the negative 2 times dc dt. Now I have dc dt. We just figured out what theta was, didn't we? Theta was, we did it using tangent, but we can also just use it using sine. No, we can. So that is sine of, what is that one? Oh, this should be something fairly obvious. Pi over 6. So theta is equal to pi over 6. And I did that just by doing sine inverse of 1 over 2, or 100 over 200. So d theta dt is equal to negative 100 times 1 over c is 200 squared. This is going to be very large. 40,000 times 6.93. And then all of this is going to be divided by cos pi over 6. Which is 8.66. Okay, so that is negative 100 over 40. Another 400. So that is going to be negative 6.93 over 400. And then that is going to be negative 0. 0.017325. Divided by that cos pi over 6, and the number we're going to end up with is negative 0.02. So, theoretically, I'm going to just erase a little bit so I can more clearly write my answer for you guys to see. Okay. And so this is measured in radians right now. So theta is changing, or is decreasing, so that makes sense. We've got this negative sign here. Theta is decreasing at a rate of 0.02 radians per second. Okie dokies. I have to get out of here. Are there any quick questions before I leave? Awesome. Yeah, thank you guys so much for coming. I hope you guys have a wonderful week, and I hope your midterm exam goes very, very well. Have a wonderful evening, guys.